Hi, in this video we are going to study the parametrization of plane curves using polar coordinates. We recall that a parametrized plane curve was a function defined on an interval I and taking values on the plane. We sent every value t of that interval to a point of that plane. But so far we have assumed the Cartesian system of coordinates on the plane. That is, every point of the plane is characterized by two numbers, the horizontal and vertical distances to the origin, taking into account the sign. But there are other ways of giving coordinates on the plane. Another one, very famous, is the polar coordinate system. In this system, every point is characterized by two numbers, and geometrically the definition is as follows. The first number, ρ, is the distance of that point to the origin, and the second is the angle of the ray joining that point to the origin with respect to the horizontal angle. That's theta. ρ, as a distance, is a non-negative number, whereas theta can take any real value. But be careful, there are some indeterminations. For example, for any value of the angle, ρ equals 0 gives the point 0, 0, the origin. And for every value of ρ, the angles theta and theta plus a multiple of 2 pi give the same point. There are formulas to give the transformation from polar to Cartesian coordinates. That is, if we have a point with polar coordinates ρ and theta, the Cartesian coordinates are related using some trigonometric functions. The formulas are in the blue box. And conversely, if one has the Cartesian coordinates of a point, the polar coordinates are recovered using some trigonometry. And the formulas are those in the blue box again. We can define now parametrized curves using these polar coordinates. The definition is the same. One assigns to every value t of the interval I two numbers, ρ and theta. But it's very usual to find simpler parametrizations using polar coordinates. Parametrizations of the type t sent to ρ of t, t. That is, the function ρ is a function of the angle. Geometrically, that means that for every value of the angle, the point of the curve of that angle is at distance ρ of theta to the origin. But be careful with the determinations we mentioned before. We now see some examples. The simplest one is ρ of theta equals a constant, and it's not difficult to see that the trace of that curve is a circle. Actually, the radius of that circle is the constant r. Another simple function is ρ theta equals theta. If theta goes from 0 to 2 pi, one recovers a piece of a spiral. Actually, there is an indetermination precisely at the value 2 pi. But that indetermination can be solved using continuity. And now we can go from 0 to 4 pi. Or even bigger. We can go till infinity, and we have a very famous spiral called the Archimedean Spiral. For the function ρ theta equals 1 over theta, we have again a spiral, and this one is called the hyperbolic spiral. For the exponential function, in this case for the constant 1.2, we have another spiral called logarithmic or exponential spiral, and that's very commonly found in nature. For example, snails. Another nice example is the function ρ theta equals the cosinus of a multiple of theta. For example, for k equals to 1, one has a circle. For k equals to 2, we have a flower of 4 petals. For 3 and 4, we have flowers of 3 and 8 petals respectively. And in general, for k odd, we have k petals, and k even gives a flower of 2k petals. If one takes the square root of a previous function, then the trace of the curve is a flower with the right number of petals. For the value k equals 2, we have a 2 flower, And this curve is very famous. It's called the Lemniscate. It's the symbol of the infinity. If we add a constant to the function cosinus of a multiple of theta, for a big enough r, then we have roses. These are the roses you get with different values of r and k. There are a lot of examples of curves in architecture that are of the previous types. For example, in this capital of a Greek column, or these stairs designed by Gaudí, or this rose window from a cathedral. They are beautiful, aren't they?